Hey everyone, it's Greg Needell from REV Robotics. At the beginning of every season, when FTC kicks off, myself and a few other REV employees, what we like to do is take the first weekend and brainstorm and build some quick prototypes to give you and your team some ideas for the season. Our goal is not to tell you what to build or to give you the solution to the game or rob you of your aha, but the goal is really to show you what you can learn really quickly, maybe give you some things that you and your team can take and talk about amongst your team, so when you go into your prototyping process, maybe you start one step further. Especially now with COVID, where in-person meetings might be limited, we felt like more than ever, this might be a real service to the community. So what you're about to see is a combination of all the prototypes that we built during the first weekend of Ultimate Goal. And if you've got any questions, feel free to type them in the comments of the video or reach out to us. We're going to be documenting each one of the individual prototypes on our new documentation site at docs.revrobotics.com, and we look forward to seeing what you can build this season. Stay safe, and we'll see you soon.
The drivetrain is probably going to be one of the first decisions that your team is going to make, and depending on the season, can be a make or break moment for the team. Luckily for Ultimate Goal, it looks like that's not going to be the case. The field itself is relatively flat. There's not anything that's going to be largely in your way, so it should make it easy to be able to just pick a drivetrain and being able to go from there. Within the REV build system, we do have a couple of really good options that are available for you. So if you happen to have already have a FTC Starter Kit V3, you can end up going ahead and today build our differential drivetrain right out of the box using our C channel and get this ready to go for your programming team to be able to prototype some intakes potentially off the front, because it's really important to being able to do that for manipulating of game pieces. And this would be a really, really solid base for you to be able to go with. Also, your team can choose to go with a Mecanum chassis. So not only do we have a Mecanum chassis kit available through our store today, but also if you happen to have the Starter Kit V3, it only takes a couple of motors and the Mecanum wheels to be able to run from what you would already have within your starter kit. The differences between the two is with the Mecanum chassis, you're going to get a little bit more maneuverability. You're able to move side to side and strafe, as well as into any vector direction, which could be advantageous for being able to line up to the goal if you happen to be shooting, or maybe going ahead and picking up any of those game pieces that happen to be moving around the field. With the tank drive though, you do get a number of options that are really good for pushing, for doing a little bit of defense. You're not able to kind of get shoved from the side as much as you can with a Mecanum chassis due to the way that the rollers on Mecanum wheels are set up. We also really like having the Omni wheels on the back of the drivetrain, because it gives you, basically your turning radius is moved forward on your robot, making it where it's able to pivot around really, really easily, and gives you some of that maneuverability that maybe you would lose within a traditional tank drive. Either way, choosing the drivetrain that you're able to utilize through the FTC Starter Kit V3 or the Mecanum drivetrain, you'll be able to go pretty far with Ultimate Goal. The other really nice thing is we've gone ahead and unveiled new documentation through docs.revrobotics.com. Not only does this have information on our control system and our overall build system, but you can also find step-by-step build guides for both our differential drivetrain and the Mecanum drivetrain. So regardless what choice you have, we have instructions to be able to help you get on your way to have a successful season for Ultimate Goal. So with that, just make a decision, be able to make that as your place to be able to move forward and end up having a great competition season. So one of the things that we wanted to try was we actually took our gripper from Skystone. So with Skystone, you didn't necessarily want to be able to attack the stones from the front when they were lined up in autonomous mode. So we wanted to kind of have something that could go over, pick them up, and then grab them and move with them. And so we wanted to try to kind of give that a go. This basically has just been set up. We just changed some of the limits and kind of have left the distances the same. And it seems to actually work okay for picking up these discs in the wider kind of orientation. So let's go ahead and take a look at how this exactly works. So basically you have like this link, you have a linkage with this on a little bit of a hinge. It's two bearings with a shaft kind of running through here. I'm going to be able to kind of hold on to these. So more or less we just have it where it's in its fully open position. We close this down and basically this pinches the whole system together, which is able to hold this all in. And it kind of holds it okay with a single one, and here you're able to shake it a little bit. The inherent problem actually comes in when you start to add in more of these. So you start going up to 2, and you do the pinch, and then you kind of go ahead, and then they're going to start to kind of go around. So like you could see like your robot, even though it's a flat field, kind of moving around, and then this is going to eventually go awry. And especially if like our original idea and kind of concept here was that you kind of pick this up and then move this probably fairly quickly, and you can already see that this one is kind of loose within the container. So likely there would need to be some tweaks and changes to this to be able to get it to kind of do what we wanted to do. Looking at some of the progress that we're doing on our conveyors, this might not be the direction that we want to be heading in because of how well some of the conveyor concepts are working. So this would need a little bit more iteration to kind of move from there. So if your team is looking at doing something like this, take this as a base, but there is going to need to be a little bit of thought and work on this guy. So we're just going to kind of set him aside for now and more look at what we've been working on with a roller intake. So this is really kind of a straightforward thing. We just have a couple of pieces of extrusion with a shaft and a stack up of our 90mm traction wheels and a core hex motor driving it. One of the things that we've been able to find, if we can get this thing running here really quick, is the core hex motor. It seems to work pretty well for picking these things up. The wheels themselves, or the rings themselves, seem to want to just kind of move with very little force. So you could see having this on the front of your robot with like a dead stop with this kind of maybe hinged or sprung down, just running right into these and being able to kind of suck them up. The one thing that has been kind of a little bit of an issue though is like, there's the potential of there being that force stack in the middle. So if you wanted to go in and pick off of those, this really doesn't do that great of a job of being able to pick up each one individually. Mainly because sometimes when you're running through this, it will grab onto two, and then you can get into a situation where it's doing something like this. So you're going to need to have a way of being able to kick out some of the ones that are a little bit higher, or confirm that this is going to be sitting at the correct height to be able to pick them up when they're in a stack like that. The last thing that we kind of wanted to try with one of these is that we were looking at doing kind of maybe one of the gear intakes, similar to what was done with the FRC teams during the Steamworks game. And so with that, if we give this the same run, really we were looking at having it where something would kind of be able to do this. So without having any compression on the top, these things really don't seem to want to run with this steep of an angle for these wheels. So what we would likely need to do is either increase the speed that are going into these wheels themselves, and also probably cut down on the angle that these are working with. So probably switching from the 90mm wheels down to something that's probably 60mm, or maybe even the 30mm wheel would work a heck of a lot better for what we're trying to achieve with this guy. So with that, we're going to kind of take some of the things that we learned here, and we're going to go ahead and implement them onto one of our Mecanum chassis, and then see what we can get from there. We'll check in with you guys back in a couple of hours once we get that prototype more up and running and ready to go. We kind of took this one a little bit to the next level. We wanted to get an intake onto a chassis, and then kept finding really kind of some cool things that we could do, and really wanted to flesh this idea a little bit further out. So we have our Mecanum drivetrain kit is the base that we're building everything off of here. And we pretty much are taking the concept that we were utilizing beforehand, which was going to be wheels on kind of an outrigger that would head out of the front of the machine here, and kind of took it to the next steps. We moved from our 90mm wheels down to a smaller wheel, but then also have made some other changes on the inside of here. So let's go ahead and take a look at kind of what we've done with this one. So we're using the open front of the chassis here. So if we actually flip this up, so this armature kind of rotates about the same way that our little test system did. And we kind of can run everything back from this motor back here. So we have an HD hex motor running into an ultraplanetary. We are using a 5-to-1 over here on our ultraplanetary gearbox to kind of get that increased speed, since we're going to be running this kit at a 20-to-1 gear ratio. So it's going to be quite a fast little drivetrain. So we want to increase our roller speed to match that. So this is our main roller. This guy is going to come and pull in, but if you go from the motor here, this chain drives into the back rollers here, and these two are chained together so they can run in the same direction. The idea with this is so that these will end up kind of riding and kicking this up and outward, kind of in a similar way that a lot of the gear mechanisms for Steamworks kind of worked, is kind of going in that route. This then goes over to our pulley over here that we have sandwiched in on this side, that then runs this belt up to our gear that is up here that then meshes with another gear so that we're able to change the direction of this front roller. Because the front roller and these back rollers need to run in opposite directions for us to get the needed outcome. This thing actually, we were really, really surprised, and it's part of the reason why we kept kind of iterating on this about how much progress we were actually making by doing like little iterations on things. So going with the 60 millimeter wheels and going with little baby 30s, and then we kind of took a guess on what this gap would need to be, and got some pretty impressive results out of this. So let's kind of give this a try. Oh, and one last thing before we kind of give this a go, we're using a lap bracket here on top of these two pieces of extrusion to kind of hold this where it needs to go. One of the things that we would likely probably want to do is add another bracket somewhere to be able to keep this from riding too low. But with that, let's kind of give this a start and kind of kick this forward. So once this is running, these things kind of, they very, very easily kind of run in and want to just pop right out and up, which is actually pretty nifty, especially if you wanted to hand this off to some sort of area. The one thing that can happen though, as you can see right here, that if this does not have enough downforce, it will kind of skip sometimes until it wants to ride up. And then the other thing too, we've noticed that needs a bit of working through and improvement, is when you put two of them in here, it will jam until you give it basically enough juice. So there needs to be a little bit of refinement and iteration on kind of what this is to make it work more consistently. Trying to pick up two at once definitely is going to cause us some issues. And then also there's likely some iteration that needs to happen with this gap. Maybe it's moving one of these to a slightly larger wheel. Maybe it's kind of closing this a little bit or kind of tinkering with this distance, because from time to time they will get kind of caught in here, or maybe it's putting a guard or something in that position. But this is kind of a really cool spot where you can take this and maybe iterate on it and find something else that would work a little bit better specifically with your machine. We're pretty happy with it so far. But take a look at this to get some ideas from there. Check out some of the other robots that we took inspiration from, specifically from Steamworks. I think 2848's robot is one that would definitely led to a lot of inspiration for this one. But you can end up taking a look at those and see if you're able to put together a similar intake onto your robot.
We've had a little bit of time to work on our two conveyor prototypes that we talked about during our live stream. So I wanted to show two of them off to you. So the first one that we built, this is a polycord based one, and we use the REV polycord here. It comes in a roll, and there are little tiny barbs that allow you to join this, so you can make these lengths any length you want, and it's kind of sticky and has a pretty good, friction on that. But the purpose of this was just to kind of show what you could do for like a layer of belting. So there's two different things here. Obviously, you can put them on the top, and you can have them go. That's good. So that works okay, but the really thing that we wanted to kind of look at here, because that's just going to fall off, is kind of what happens when you pinch the disc in between the cord and just a flat material. We're just using cardboard. This whole weekend's all about just fast prototypes that you can do. This frame's built out of just extrusion with a core hex motor. There's not a lot here, but I'm going to show you kind of what this can do. So. All right, so you can see that's pretty steady. There's a couple things here. At low power, they obviously don't move as smooth, and then with a type of system like this, you have to worry about kind of constant pressure in the middle. But what I do want to do is I want to turn this thing on full power, and I'll show you this thing can actually put them out pretty fast. And we're controlling this thing with a expansion hub hooked to a computer. Mack's just off camera controlling this, so it's something you can do really easily. There's no programming involved here. So Mack, you want to turn it on? All right, so that's nice and flat. So what I want to take a look at is, obviously if you're going to be doing this, the most likely scenario would be this would be coming from some sort of intake up to some sort of shooter. So we're going to kind of look at an angle. This is probably close to 45 degrees. So. And we can go a little bit steeper. But I'd say that's a pretty good first prototype that shows these are pretty easy to convey. So that's this polycord prototype. The next prototype version of this that we worked on was more of our open style. And this open style, what we used for this is we used timing belt. And we have this really cool little timing belt pulley system that allows you to build your own pulleys to whatever width you want. So we have centers and end caps. And because all of our belts are 9 millimeters wide, or increments of 9 millimeters wide, that plays really nice, so you can build some of these like fatter kind of center ones to run double belts on a single pulley. What we found in prototyping, we went and grabbed some of this timing belt, and it has a really nice coefficient of friction on the back of the belt for these. And so the nice thing is that this is a little bit more compact than the other one, and it's also a little bit easier to control. So I'm going to hook up a motor here. And the other thing to point out with this prototype is that we used chain, crossing chain on the bottom, so that we're using one motor to drive both belts, but both belts are actually spinning opposite directions. So when this is in here, these rings are not spinning, they're just actually being conveyed. So Mac, do you want to turn this one on? All right. So as you can see, that one works really, really smooth. And I mean, this is, because of the space and the size that this takes up, this is something that you should really easily be able to find, because it is not much thicker than two rings in thickness. So, and also you're able to go almost straight vertical with this type of system. I mean, you probably can go straight vertical if you try. I haven't tried this on camera, but you know, there is almost enough friction that without anything holding it in on the bottom, you can actually do them upside down. So this one, this is like what I would consider to be like an A-class quick prototype. I feel like we learned enough just playing around and building this thing in about an hour that this type of system will work for this year's game if you need to move rings around. And it's really just some timing belt pulleys and bearing mounts and pretty easy stuff. We're using a piece of the coroplast, but I think that a piece of Lexan or cardboard or anything else that's kind of slippery in here will be pretty good. We did not really have to play with the distance here much. It seems pretty, because these rings are so flexible in general, it feels like the tolerances for how they can compress didn't really matter that much. So we just kind of put it in, adjusted them, and it worked. So Mac, you want to just turn that on again just for fun? So I could see this feeding to a shooter as fast as your shooter could kick them out. So we're going to move on to the next prototypes, and we'll check back in a little bit later. Thanks. One of the things we talked about during our game breakdown was how important it is to be able to manipulate these wobble goals. So the nice thing about the rules this year is it allows you to hold one of these before the match starts, meaning that all you have to do is make something that you can latch onto this on your robot, and you can let it go during autonomous mode, and then there's some other simple ways to manipulate this. So originally, during the stream, I drew this little latch where I figured there'd be a cutout opening with a servo that could hold it back and then kick it out. This is something that anybody could build on the side of the robot. Originally I was thinking we laser cut or 3D print or something, but when I got into it, I realized that a small piece of a couple brackets and some extrusion and a servo literally does everything that you need to do. So here's kind of the idea that this would work on. So you've got the goal, and before the match starts, you just take the goal, put it there. I'm using the edge of this cap as kind of a stop because you can already see it kind of supports it just on the edge of the cap. This is not heavy, this is not a lot of weight, and then you can also take this bar and kind of lock it in on 3 positions. I think the angle's not right, and I think that there needs to be some finesse work here, but really this is all about trying this concept. We really like these 10-minute quick concepts. So I'm going to demonstrate this for you. So pre-match, you put it in, you set it up. I'm just using the REV Smart Servo and our servo programmer as just the quick way to do this. So I'm going to plug it in. You can imagine this on the side of your robot. It's holding it, holding it, holding it, and then when you get to the position, it goes and drops it, right? And so there's definitely some finesse here, but the ability to have something that you can just manually with your hand pinch that goal in place, and then the servo just spins or holds it back and then can just spin around and knock it out of your grip to make sure you drop it is totally great. I added a little bit of our slot cover here just for a little bit of extra grip. Like I said, if I spent more than 10 minutes on this, I think we could make it better, but part of the prototyping process is really going fast, right? So check out something like this for your gripper. The next prototype that we did is actually, we took one of our lifts that we had built previously. Over this summer, we had some interns working with us, and they built some really cool new iterations of REV linear motion systems. We're going to have some documentation on the lift itself. This is using an ultraplanetary and a cabling system. This is actually very much like an FRC lift, but it's built with all of our standard plastic linear motion parts. And so what we did quickly here today was we just added these little flip down arms, right? So this bar was already on this carriage here, and we added these little arms. This is just using some hinges and a thing. And the same idea here was, how would you get this out of the goal, out of the field towards the end of the match? And the same idea was, if you could just make a wide V entry, and imagine this on the back of a robot, you just drive up to a thing and then lift up. You can lift it up, right? You need to, in order to get the points to get this out of the field at the end of the match, you need to lift this by at least 1 foot. So these are a little taller than 1 foot on their own. So as you can see, this is 2 stages. So this is 1 stage, and then the carriage is the 2nd stage. And so if this was on the back of your robot, you could just drive up to the wall and then just put it right back down. And this is a pretty fast mechanism. And you can do this. There's no control loop here. This again is just being run from our expansion hub hooked to a laptop to demonstrate the purpose. But if this was tucked in at the beginning of the match, so you're inside the 18, these can flip out based on gravity, or you can put a servo here. But with a really basic kind of little, either just a pinchy grip or just some type of thing you can run into the goal, grabbing by these caps allow for a lot more of a compact mechanism than maybe if you had to kind of go all the way up underneath. So that's all we've got for these little manipulators. And if you have any questions, feel free to send us an email, and there'll be some documentation on this as the week goes on at docs.revrobotics.com. So this is our first iteration of a super fast shooter prototype. All we've done here is we've used some 15mm extrusion with brackets. a ultraplanetary and one of our grip wheels to just do it. We've added a couple extra gears in here as a little bit of extra flywheel weight just to do some testing. This is a 5-to-1 gear reduction on the ultraplanetary. So I'm going to show you what this is. Just because we're dealing with shooters and spinning flywheel, it's always important to be safe. So I'm going to wear safety glasses for this, and we're just going to kind of see how this goes. So as you can see, 5-to-1 doesn't really seem like it's got enough speed. The shots themselves are very consistent, but we were only shooting about 18 inches. We're going to swap that out to a 3-to-1 and see what happens. All right, so we've switched this ultraplanetary to a 3-to-1 gear reduction instead of 5-to-1. Everything else is the same, and we're going to see how the results of this one go. So this time, instead of going about 18 inches, it looks like they were going about 3 feet, 4 feet. So now we're kind of in two different modes. Obviously, that's not far enough to try to sink a 12-foot shot. So we're going to try a couple different things. I think the first thing I'm going to try is taking this to 1-to-1, just removing the gearbox completely and see what 1-to-1 on the wheel does. That might not be a great solution, but we're going to give that a shot first before we start making other adjustments to the setup. When it comes to trying to work through collecting data to see how it changes, whether it improves or not, it's really important to only change one variable at a time. So in this case, I'm not changing compression, I'm not changing the wheel. All we're doing is changing the gearbox. So we'll make those changes. I'll be right back. All right, so we've swapped this out to no gear ratio. So this is 1-to-1, but it's going through an ultraplanetary, so it's using the bearing on the output shaft to do a good support. If everything goes well, you're probably not even going to see where these land. So all right, so as you can tell, that's a lot closer to what we were expecting performance. But one of the things that we're having a problem with here is this thing is vibrating like crazy. And when you're trying to spin the motor so fast with so much flywheel, it's creating a lot of vibration. And since we don't have this really secure, it's just a really light duty frame, I think we're gonna have to kind of go up in rigidity for the next prototype. The other thing that I think that we're going to want to try really quick, maybe still on this prototype, is maybe add a second wheel here. The reason we want to try to maybe add a second wheel is so that when I tried to push multiple through at the same time, you could see that the second disc dropped a little bit from the first one, and that's generally an indication that you're really at the edge of speed. And so if we can increase the disc across two different wheels, that might allow this to recover, which means you'll be able to shoot these quite a bit faster. So give me a quick second, I'm gonna mount another motor and we'll come back and test it. All right, so we've added another motor that's also at 1-to-1, and we're gonna test this. I will say that I turned this on before I turned the camera on, and while it fires really well, it's also a little bit terrifying based on the amount of non-support that you have here. So if you build this setup, please make sure to be safe. We're gonna probably after this take this and build it more rigid to really test it, because this is about as far as I'm willing to take this as is. So Mac, you want to turn it on? All right. So as you can see, this thing's shooting like a laser beam off the side. We have a wall over here, so I don't exactly know how far away it is. I mean, I know it's at least 6 feet from the center of this to that wall, and it's still climbing at the point that it hits that wall. So I think the next thing we'll do is maybe I'll take this out to the field and we'll do a little bit of just a distance test where we can do it, but I really do want to do some more security on this right after that quick test. All right, so we brought this prototype out into the field. We were just really excited to see what it could do on the field. So I brought it out here. Mack's going to turn it on, and we're just going to fire a couple shots, and then we're going to go kind of reinforce it if it does well and work on improvements. So, all right. So you can see there's like a curve to this shot, so I'm going to try to compensate. So it wasn't going as great as I hoped it was going to go, but I think that a lot of that, some of that has to do with the heavy vibration that we're doing in here, where we haven't, it's really loose and wobbly, so I really want to tighten this up. It definitely has the distance, but right now it's just really, really inconsistent on the shot, and part of that might have to be with the way that I'm feeding it in, the wheels and everything. We haven't really done much work on this compression at all, because we were trying to only modify one variable at a time, but this gives us enough to work on that I think we're going to spend some time tonight and maybe into tomorrow a little bit building a slightly more robust version of this shooter, because it's promising enough that we're going to take it to that next level. So we spent a bunch of time working on this shooter prototype. Actually, we decided to just completely rebuild it from scratch. And really the focus on here was rigidity. This thing vibrated a ton, and when you're spinning a wheel at between 5,000 and 6,000 RPM, vibration is everything. So this time we used some of our pitch plate along with our hex bearing blocks, so that now you have a top and bottom ball bearing. That makes this much smoother. But also by boxing in the frame here, this whole thing is a lot more rigid. Rigidity, I think, is going to be the key with consistency here. So we have done a little bit of adjustment on the compression, but I'll get into that. But let's take a look at kind of where we're at. Matt? I can consistently hit that logo. There we go. So not too bad for a prototype that I'm holding in my hand. I think we may do a little bit more testing on this, where we actually try to play with the angle and put something here so that we can actually mount it to see if it gets consistency. One of the other things that we noticed a lot, and you might have saw me adjust it during the video, is that when they come out like this, they actually get a kind of a curve to them. So that is something that we're going to have to kind of take, the teams are going to have to take a look at. Also, this is just running raw motor control based on the interface software. So I think that when we start looking at wheels, you definitely want to look at like the PID and actually controlling the velocity on these. All that's going to really help with consistency. I'll take this back into our studio, kind of walk you through some more of it, and we'll check back in. So shooting and shooting prototypes is always a lot of fun. I thought I wanted to go over this just a little bit so you got a deeper, closer look at it. As I mentioned before, we're running 2 HD hex motors, 1-to-1 through ultraplanetaries. The nice part about that is it gives you a really nice bearing when you're going fast speeds. You know, these wheels 1-to-1 are between 5,000 and 6,000 RPM, so that's quite a bit. We're using bar up on top, so this whole thing is really rigid, but it's really important to point out, like, we're using a ball bearing block on the top. So this is our mounted hex bearing. One of the things I really wanted to point out here in this video was about compression, right? So compression is all about, you know, you want no slippage, and it's how much energy exerts to it. We are able to slide this wall in and out, so we were doing this on the fly when we were shooting on the field, and when I got to the most consistent shots, the compression is actually quite a bit. So this is actually squeezed down quite a lot, and it didn't seem like it slowed the motors down, and they were actually shooting rather straight. So there's definitely a lot more testing that would have to get done to tune this in. We've decided to kind of leave this as is, just kind of leaving this from an idea inspiration standpoint, but we really like the performance of the 2-motor solution with the 2 wheels in line. There's no grip here. This is all very nice and smooth on that side. I know in the past some people have, you know, said that maybe putting some friction material here, you might be able to get away with less compression if there's a friction material here. And then the other thing too is in the software. So we were running this straight voltage control, so just hooked up all the way. We weren't monitoring our battery voltage. We weren't monitoring any part of that. So you really, really want to be able to control the velocity on this, because as a match goes on, as the event goes on, you don't want to just randomly have your shot changing how far it can go based on whether you have a good battery or not. So you really want to do closed loop control using the encoders on these motors. We're going to try to get an example up of how to do that on the docks up here in the next week or so. And but you know, this is a good framework or a good place to start. There are going to be lots and lots of solutions on how to shoot these and score into the high goal. So this is just one example from less than 48 hours of tinkering around with it. And so if you've got any questions, feel free to shoot us an email, and there'll be more information about this shooter and our other prototypes on our documentation site, docs.revrobotics.com, and there'll be a link for our prototyping. So we'll check back in later to wrap this up.
Tell me when.
Go ahead. We've just finished up 2 days of building, and we've come up with a bunch of different prototypes here. We just wanted to do a quick recap as we close out our prototyping time for the day. So this was our simple elevator lift with a gravity flip down so that you could pick up and move the wobble goal, both in autonomous mode but also out of the field towards the end of the match. And then we also have this conveyor here that this was our open belt using timing belt that did a really good job of being really low profile but also really smooth conveying of these, and the timing belt to the frictional coefficient was really good on that.
And over here we have our Mecanum chassis that we were running with the pasta roller style intake on there that did a pretty good job of collecting and then flipping our rings into the position so that we're able to end up transferring them to some other system potentially to score them a little bit later.
Yeah. And then finally, you know, the kind of the fun one really, we did a shooter with this prototype which is running 2 HD hex motors at 1-to-1 using our 90 millimeter grip wheels in a very stiffened chassis. We were able to shoot almost the complete static shot from there to the goal. We got it a few times, but it definitely would need some tuning before we could say, you know, we could hit our raw time every single time. But
yeah, and so what we're planning on doing is we're going to take photos of these. We're going to take some more of the documentation and things that we've created across these couple of videos and putting them up on our new docs site. So docs.revrobotics.com. You should be able to find not only the build guide, for example, for the Mecanum drivetrain, but also some hints and some photos from behind the scenes on what these machines can actually do to be able to take them as inspiration for your machine for this year.
yeah, so, and you know, remember, we were trying not to provide you a solution. We're just trying to provide you with a couple ideas and inspiration for you to think about while you may not be able to meet with your team. And so if we could do this in only a couple days, we really look forward to seeing what you can do over the course of the season. So stay safe, have fun, and we'll see you soon.
Adios, guys. The little dance we're going to turn into a GIF.
No, we're gonna throw those all at the end of the 16-minute all-together video that we're gonna put.
Just do the twist, do the twist. Now tell me, baby, do you like it like this?